say me, yeah. I was about to throw something.
Okay. Can we continue? Yeah. Right. A metal rod of length 1.05 is moving at a velocity of 25 meters per second in a direction perpendicular to a uniform magnetic field of flux density that. Right, so here's my field here. I'll try and draw it in 3 dimensions if I can. It might be a little easier. Okay, so here's my field. And it's B equals 2.6 times 10 to the minus 2 Tesla. And then what you have here is a metal rod. And it is 1.05 meters long. And it's moving perpendicular, so it's moving up. So it's like it's moving up the back wall there. And it's moving up at a rate of 25.5 meters per second. And the length here is 1.05 meters. And they want to know what's the current here. Now, the EMF. So the EMF, according to Faraday, is minus N delta phi over delta T. The N here is 1, because it's just one wire. And I don't really care about the minus, because that's just telling me the direction. So that's just equal to this, which is equal to the change in BA over T. Now this is the key question. What is changing here, the B or the A?
The A.
A. If this is 1.05 meters and it moves 25 meters per second, then it means in 1 second it makes an area of 1.05 times 25.5. That's the area change per second. You see, if you think about it like this, it's like B delta A over delta T. That's like saying how quickly the area changes. How much area do we get per second? So the answer will be 2.6 times 10 to the minus 2 times 25.5 times 1.05. What's that, please? Well, let me double check, because I know they do it a different way in the book. .69? 0.696. Yeah, but you that's what you do in class. And actually, that's a new formula. That's which one? Yeah, that's a new formula. They only added that to the formula book last year. So my slides, I don't use this formula because I actually did not know they just stuck that into the formula book. Because usually what happens is I look through the formula book, they send each year, and I'm like, oh, look, new formula, that's interesting. But you didn't need this formula because you got the same answer. Yeah, that's what I've done. I suppose the point I'm trying to make, Monica, is that we already have so many formulas in physics. I don't really want to introduce to a class a new formula when it's really just the same as this. You know what I mean? Yeah. But I mean, of course, you can use that one in the exam. And you're right, it is just, here it's just, you've spotted that this is B, this is L, and this is V. So you could actually make that a formula. You could actually say the EMF is BLV. But I mean, that is actually, after a little bit of work, you can see it actually is the same thing. How many marks is this one?
4.
Yeah, it's only 2 marks, so.
So hard.
Is it though?
I mean, the field mark is a little bit low, like 2.
Yeah, a little bit.
Formula.
I mean, the atom is easier, but like 4 marks,
Well, the next one is easy, isn't it? It's just a formula. Do you want the field strength?
It's
And
easy for you.
right, I'll let you continue with the next one. So just before you do, the next one, what you have is you have iron 57.
What do you have to show?
Hold on, Andrew. You have iron 57, and the distance from the centers is 0.565, and the nucleus contains 31 neutrons. And the question is, what's the electric field strength? So what's the formula here? It's the one that says electric field strength is 1 over 4 pi epsilon 0. Or in other words, what we sometimes just call K, Q over R squared. Now this is the thing that's not clear. What's the Q?
You have to find the number of electrons.
Yeah.
Okay, multiply by
26 times 1.
But the problem is there's lots of protons.
but the electron doesn't count.
You see, I believe the question is mistyped or something is missing from it. It says, what's the electric field strength due to... Oh, snap. Guys,
Yeah,
I'm actually going to do... I'm going to let you try 9 by yourselves for a minute.
I have to do that.
You have failed it.
Yeah.
Can you try for another minute and fail again? Thank you.